A genetic algorithm, or GA, is a search heuristic inspired by the process of natural selection that belongs to the larger class of evolutionary algorithms, also known as EAs. Genetic algorithms are commonly used to find approximate solutions to optimization and search problems. They are particularly useful for problems where the search space is large and complex. 1. Population-based search genetic algorithms operate on a population of potential solutions rather than a single solution. 2. Selection solutions are selected based on their fitness, which is a measure of how good they are at solving the problem. 3. Crossover, also known as recombination selected solutions, are combined to produce new offspring, mixing the properties of the parents. 4. Mutation. Small random changes are introduced to offspring to maintain genetic diversity and explore new areas of the search space. And 5. Generational replacement. The population is updated with new offspring and the process repeats over multiple generations. The operation of a genetic algorithm can be summarized in the following steps. 1. Initialization, a population of candidate solutions called individuals or chromosomes, is created randomly or based on some heuristic. 2. Evaluation. Each individual in the population is evaluated using a fitness function that quantifies how well it solves the problem. 3. Selection. Individuals are selected for reproduction based on their fitness. Common selection methods include roulette wheel selection, tournament selection, and rank-based selection. 4. Crossover or recombination. Selected individuals or parents are paired and crossover is performed to create new offspring. Crossover involves swapping segments of the parent's genetic information to produce children. 5. Mutation. Random changes are applied to the offspring with a small probability. Mutation helps maintain diversity within the population and allows the algorithm to explore new areas of the search space. 6. Replacement. The new offspring replace some or all of the current population, forming the next generation. And 7. Termination. The process repeats for a predefined number of generations or until a termination condition is met, like a solution with acceptable fitness is found or improvement stagnates. Example of genetic algorithm. Solving the traveling salesman problem, TSP. The traveling salesman problem, or TSP, involves finding the shortest possible route that visits a set of cities exactly once and returns to the original city. 1. Each individual or chromosome represents a possible route. For example, a chromosome might be an ordered list of cities. 2. Generate an initial population of random routes. 3. The fitness of a route is the inverse of its total distance. So, shorter routes have higher fitness values. 4. Select routes for reproduction based on their fitness. For example, using roulette wheel selection where routes with shorter distances have higher probabilities of being selected. 5. Apply crossover to selected routes to produce new routes. For TSP, a common crossover method is order crossover, OX, which preserves the order of cities. 6. Apply mutation to the new routes. A common mutation method for TSP is swapping two cities in the route. 7. Replace the old population with the new routes. 8. Repeat the process for a set number of generations or until the shortest route found remains unchanged for a certain number of generations. Applications of genetic algorithms. 1. Solving complex optimization problems in engineering, economics, logistics, and more. 2. Feature selection, hyperparameter tuning, and evolving neural network architectures. 3. Solving scheduling problems, such as job shop scheduling, where tasks need to be assigned to resources efficiently. 4. Automated design of structures, circuits, and other engineered systems. 5. Evolving strategies for playing games and simulations. Advantages and challenges. Capable of finding good solutions for complex multimodal problems, does not require gradient information or continuity in the search space, can handle a variety of optimization problems and constraints, computationally intensive, especially for large populations and many generations, requires careful tuning of parameters, such as population size and mutation rate, may converge prematurely to suboptimal solutions without sufficient diversity. Conclusion. Genetic algorithms are powerful, nature-inspired optimization techniques that simulate the process of natural selection to solve complex problems. By leveraging mechanisms such as selection, crossover, and mutation, JAS can explore large search spaces and evolve solutions that are difficult to obtain using traditional optimization methods. Despite their computational demands and need for parameter tuning, JAS are widely used in various fields for their robustness and versatility. For further explanations of AI terminology, hop over to Ai-Epicentre.com.